Hi everyone. In this lecture, I will be looking at two special continuous distributions. The first one is the uniform distribution. I want to start off with just a quick example of where it would be relevant. So consider the random variable y representing the arrival time of a bus at a bus stop. Assume the arrival time is between 8 and 10 past 8 a.m. and that the probability that the bus will arrive in any given subinterval of time is proportional only to the length of the subinterval. So you could plot the graph like this. This is the 10-minute interval, and what this tells us is that the probability of the bus arriving in the first 2-minute period, A1 in this example, is exactly the same as it arriving in any other 2-minute period. For example, A2, the probability of arriving between 6 and 8 minutes past 8 is the same as arriving between 1 and 2 minutes past 8. And the probability of arriving in a 1-minute interval is just half of arriving in a 2-minute interval. So you have this case of direct proportion. This is a typical uniform distribution, and the probability density function is as follows. So this is the definition of a uniform distribution. Remember, distributions are unique, so if you have a PDF that looks like this, then it has to be uniform. This is the shorthand form, and we already touched on this in the previous lecture, so we're just going to move on. The graph is always going to look like this. It's a straight line at 1 over b minus a. In a test, you will be given a section like this in your table of formulas, so you don't have to memorize anything that's in this table here. One of the required outcomes for this distribution is that you need to be able to derive the CDF of x. We're going to do that. We've done the derivation of a CDF before, so it's just a quick recap. If this is the probability density function, we can see immediately that we have three different regions that we need to consider. So we need to just start off with the definition of a CDF, which is just this. Now suppose we have a value of y that's in region 1. The area under the graph for any value of y between minus infinity and a is 0. You can see the line is there. So we're not even going to bother with that integral. We're going to start with region 2. If I give you any value of y between a and b, it'll be in region 2. And if you wanted to find the area to the left of that value of y, you just integrate from minus infinity to y. So from minus infinity to a, your PDF is just 0. So you plug it in there. Now to get the area between a and that value of y, you integrate from a to y. Here we've just taken out 1 over b minus a because it is a constant, so it doesn't need to be in there. This is the integral. Remember, the integral of a constant, in this case it's 1, is just t. Now if you substitute the upper and lower limit, you end up with y over b minus a over b minus a. And you can simplify this, and this gives you the CDF. We didn't do this part for b explicitly because we know it's a valid PDF, so the area to the left of any value in region 3 is going to be 1. So this is the general way of finding a CDF given a PDF. Now we're going to have a look at an example. So in this example, we're studying low bids for shipping contracts. So let's just have a look at the question. In this question, they tell us that these low bids for bidding contracts follow a uniform distribution between 20 and 25. You can pause the video to read it in detail, but I'm just going to get straight into it. We will also find the probability that the low bid in the next interstate shipping contract is below 22,000. So if we let x be the random variable denoting low bits, we're going to do it in thousands. Then we have been told in the question that x has a uniform distribution 20, 25. So the nice thing about chapter 4 is a lot of the times you will actually be told the distribution. You don't have to look for special characteristics in the experiment. So we've been asked to find what's the probability that x is less than 22. Or in other words, less than or equal to 22 if you're given the CDF, because these things are equivalent for a continuous random variable. So one approach you could have followed is using the integral. So as I told you, in a test or an exam, you'll be given this list and you'll look for the PDF that you want. So in this case, for the continuous uniform, it's this one. And we know that A is 20 and B is 25. So if you plug it in, this is the probability density function that we get. So the difference between 20 and 25 is just 5. Okay. So now if we directly apply this formula, we move on to this. We're going to find the area under 1 over 5 between 20 and 22. Now, if you integrate, the integral is just that x, and then if you substitute 20 and 22 in place of x, you end up with that difference, which gives you 2. So it's 2 times 1 over 5, which gives you 2 over 5. Another way you could have addressed this question is by looking at the graph directly and finding the area. So in this graph, you can see it's a straight line. What you could have done is you just want the area between 20 and 22, but under the line 1 over 5. So this is a typical rectangle, so you could have just found the area of that rectangle. So this would have been 1 over 5 times 2, which gives you 2 over 5. Here is part B. I'm not going to do it here, but if you would like another practice example, you can try it in your own time, and the answer is 0.2. It's the same procedure as what I did before. I'm going to focus on C quickly. It's very straightforward. We just want to find the expected value. As I said, you will be given this in a test, so you just look for the formula for the mean. We know what A and B are, that's 20 and 25, so you just plug them in and you end up with 22.5. And that's all that you have to do. In the textbook, you'll see example 4.4 is another example where they apply the uniform distribution, and you can have a look at that if you would like a bit more practice on this. Let's have a look at the normal distribution. We've already looked at the uniform distribution, and this is how it looks typically. Now the normal distribution looks more like a bell. In real life, height is typically normally distributed, and so is weight. And if you look at the distribution, you can see that most of the density is in the middle here. So what this tells us is these observations that we have here, most of them are going to lie here. So there's going to be typical values where most of the population will lie. And then as you go towards the extremes, you have fewer and fewer observations. This is what the probability density function of a normally distributed random variable looks like. Sigma is some positive value greater than 0, and x is any value between minus infinity and x. Now, if you look at this distribution, if you wanted to find probabilities, you actually just need the value of sigma and the value of mu. Now, these have special meanings. Mu is just the mean, which is typical as you know, and sigma squared is the variance. So if you wanted to write this distribution using the shorthand notation, x follows a normal distribution, so you use the n to denote the normal, and then the parameters is mu sigma squared. So you'll always put mu first, and here you're going to put the variance. So even if you get a question that looks like this is what it's going to mean. The entire family for normal probability distributions can be described by these two parameters. So let's have a look at a few examples to see what this means. So regardless of what mu or sigma you take, you can see in every single case you have a bell-shaped curve. You can immediately see the impact of changing the variance if we focus on that first. When the variance gets bigger, so 0.215, you see the spread becomes bigger. So that 0.2 is this red one. The 1 is the green one here, so you see it's getting more spaced out. And the blue one is the one with variance of 5. It's getting even more spread out. So in other words, the larger the standard deviation, or sigma, the larger the variability, and hence the flatter the curves. Sigma squared is typically referred to as the scale parameter because it just determines the scale here, whether it's the values are spaced out or squashed together. Mu is usually called the location parameter because it pretty much tells you where the distribution is on the number line. So in this example, for the red one and even the green and the blue one, mu is equal to 0. So you can see the mean is 0. When you take mu equal to -2, it shifts the entire distribution to -2. That's why it's called the location parameter. Now, if we go back to the graph, I want to just have a look at some of the characteristics. So a normal curve is always going to be bell-shaped. The total area equals 1, and it's always symmetric around the mean. So in other words, the mean is therefore going to be equal to the median. And that means that the probability that x is less than mu is exactly the same as the probability that x is greater than mu. So either side of mu, the area is equal to 0.5. Another thing that you need to know is this special case that applies to distributions that are approximately or exactly bell-shaped. It's called the empirical rule. So studies have shown, and even mathematically now, you can actually show it, that between mu minus sigma and mu plus sigma, you'll have 68% of all the observations. So this region between mu minus sigma and mu plus sigma is exactly where observations are within 1 standard deviation from the mean. So let's look at the next part here. The probability of an observation being within 2 standard deviations of the mean. So in other words, between mu minus 2 sigma and mu plus 2 sigma is equal to 0.95. Because you expect 95% of the observations to be in that region. And you expect 99.7% of your data to lie within 3 standard deviations. So you actually expect almost all of your data to be within 3 standard deviations from the mean. So mathematically, you can write it as follows using the norm. So the probability that x minus mu inside the norm there is exactly the same as this, and I said it's approximately 0.68. You can do the same for all the other cases. And this is just a property of such a distribution that's bell-shaped. Okay, so now let's get to the fun part. What if we wanted to find probabilities? For instance, the probability between A and B. The procedure is always to integrate from A to B on the PDF. But this PDF looks crazy. Believe me, it's crazy because as a matter of fact, there's actually no standard integration techniques that can be used here. So what do we do? Well, using numerical methods, somebody, praise God for them, has already done it for mu is equal to 0 and sigma equal to 1. So in the same way that you had binomial table and Poisson tables, we actually have normal tables, and I'm going to show you how to use them in the upcoming slides. So Yay, that means no integration for you for the normal distribution at all. So this is the formal definition of the standard normal distribution. So this one is specifically called standard because the mean is 0 and the variance is 1. Okay? If the mean is not 0 and the variance is not 1, then it's a non-standard normal. So this is a very special case. And in this special case, we always use the letter Z. So it's pretty much reserved. If you see a Z, most of the time it's going to be normal unless you've made a mistake, but it's reserved for the standard normal distribution. So as I've mentioned, this is the definition in the textbook on page 181. And this is, I've already mentioned that mu is equal to 0, sigma is equal to 1, and Z is reserved for this. Now we also have special notation for the CDF. Instead of using a capital letter F and writing FZ, we use this notation here. So it's exactly the same, except instead of a capital F, we're going to use a capital letter phi. So that's just PHI, so it's just a Greek letter. This is how we're going to denote the CDF for a normal, standard normal, as a matter of fact. Not even any normal, a standard normal. It's going to be phi. So this distribution, it's so prevalent in real life, and it comes up so much that it even has its own special notation. So don't be using Z for anything else. Don't use phi for anything else except for the standard normal. As I mentioned, in the textbook you have tables. These tables give you the area to the left of any value of Z for a standard normal distribution. So this is what the table looks like. It's just a portion. This is table A.3. It is at the back of your textbook, so you can have a look at it there. I want to show you in the next slide how to use this table. Just before we have a look at a specific example, I just want to show you in this table what everything represents. So you'll see the top row and the far left corner and the far left column. Those are values of Z. This column represents the units and the tenths, and then this represents the hundredths. The values inside are your probabilities. So for any Z value, that's going to be, for example, this Z value, these probabilities represent the areas to the left of that value. So let's look at an example. Suppose we want to find the probability that Z is less than or equal to 1.25. You're going to look for 1.2 in the far left-hand corner, and then you're going to look for the hundredths in the top row. Then you're going to go across at the value of 1.2, and you're going to go down at the value of 0.05. And then where those things intersect, that is the probability to the left of 1.25. So in this case, the probability that Z is less than or equal to 1.25 is just 0.8944, exactly what we have in the table. Example 4.19 on page 182 gives a couple more examples of this. So just go and look at that example if you need a little bit more practice before you do the exercises. In this slide, we have a very interesting and useful property of this distribution that I want to highlight. So suppose I ask you to find the probability that Z is greater than or equal to 1.5. So this is just an example. Then you're going to look for the area to the right of 1.5. So that's that area shaded in blue. And obviously the tables give you areas to the left. So using the complement rule, you can just convert that into the probability of 1 minus the probability of Z being less than or equal to 1.5. And you can go straight to the tables and look for 1.50 and find the area to the left. Now, this is another way of thinking of it. Remember, this distribution is symmetric at the value 0. So what if I reflected this region? So in other words, the reflection of this blue region is this red region. Now, what's the value over here? Now, because of symmetry, the value in that position is minus 1.5. Okay, so this actually leads us to another way of finding a probability. So if I ask you to find the probability that z is greater than or equal to 1.5, it's exactly the same as the probability of z being less than or equal to minus 1.5. And you have tables for negative values of z. So instead of using the complement rule and finding this difference, you can read the value off of the table directly. So in general, if you have some value of A and you want to find the area to the right, it's exactly the same as the area to the left of minus A. Okay, so this is a property that comes in handy sometimes. If you go back to the exercise that I gave you, part C is one of these. Have a look and see if you worked it out this way, will you get the same answer? Okay. The second last thing I want to show you is how to find percentiles. So if you go back to the definition of a percentile in your textbook, it says it's that value, in this case eta p, such that the area to the left of that value is just p. So for instance, if I wanted to find the 25th percentile, okay, in this example, p has to be a value between 0 and 1. Therefore, p is equal to 0.25. That means the value, the 25th percentile, the value we're interested in, that eta 0.25, is this value on this axis, such that the area to the left is 0.25. Similarly, if I wanted the 75th percentile, p is 0.75. Therefore, the value, that 75th percentile is eta 0.75. So value on the y-axis such that the area to the left of that value is 0.75. So now I'm going to show you how to do it for the normal distribution. Okay. Now remember, we're just looking for z less than or equal to some value. So that's equivalent to looking for what value can you plug into your CDF such that the area is equal to p on the left. So remember, for the normal distribution, we use a capital letter phi. So let's have a look at the table. So as I mentioned earlier, we need to remember we have z values on the outside, and then we have probabilities on the inside. So remember, when I'm asking for a percentile, it's the same as me asking you to find a value of z. So I've given you a probability. Now you just have to find a value of z. So it's almost like going backwards from what we were doing earlier. Earlier, I gave you z. I told you to find a probability. This time, I'm asking you to do it the other way around. Okay, so let's try a quick example. So if I ask you to find the 99th percentile of z, I'm asking you to find some value, eta 0.99, such that the area is 0.99. So remember, these are actually left-hand probabilities or areas. So what you do, you start off inside the table now. Okay, and then you work outside. In this table, you're going to search for a value that's as close as possible to 0.99. And in this case, it's this one here. And then now you need to find the value of z that corresponds to this. So you're going to go backwards. So if you go across, you get 2.3. And if you go up, you get the hundredths value, which is 0.03. So the 99th percentile, therefore, is 2.33. Okay. So sometimes you're going to be given a p. That's not necessarily a nice value that you can find directly in the table, because you see you have all these different decimals here. Sometimes this p that we give you is going to lie in between two values of z. In this case, if p lies between two values, you're going to take the closest one to z. The closest z value, sorry. So in this example, this is not exactly 0.9901. But if you look at 0.99, it actually lies between 0.9898 and 0.9901. It lies in here, but it is closer to this value than to that one. So that's why we took this value. Okay. You're probably wondering, what if you get a value of p that lies perfectly in between two values? Well, even if you're not wondering, I'm going to show you. The 95th percentile is one of those special cases where if you look for p equal to 0.95 in the table, it's going to lie between two values, right in the middle. So this is where 0.95 would be, somewhere in the middle there. If you find the difference between 0.95 and this value, the difference is 0.0005. And if you find the difference between 0.95 and this value, the difference is also going to be 0.0005. So you see 0.95 lies exactly in between two values here, and therefore it's not necessarily close to either one of those. So now, which one do we pick? Now, in this special scenario, we're still going to follow the normal procedure here. We're going to go across in the appropriate row. In this case, that gives us 1.6. And then now we're going to go upward. This value lies directly between 1.64 and 1.65. So we're going to take the average, or what's exactly in the middle, which is 1.645. The 95th percentile of Z is therefore 1.645. So the probability that Z is less than or equal to 1.645 is approximately 0.95. I would like to just reflect on the implications of that useful property on percentiles now. Okay, so earlier we said that 2.33 was the 99th percentile. The area to the left is 0.99. Now the area to the right, therefore, is 0.01. And due to symmetry, the area to the left of minus 2.33 is exactly the same, which is 0.01. So what this means for you is that minus 2.33 is the first percentile. So 2.33 is the 99th, minus 2.33 is the first. So have a look at this now. 99 plus 1 gives you 100. So whatever percentile you have here, if you take the negative value, then it gives you 100 minus that thing. So we'll look at a couple more examples a little bit later. But now I just want to introduce to you some special notation that is going to be so relevant not only now, but especially in the second semester. So we have this notation, we say Z alpha. What is Z alpha? Well, graphically, Z alpha, it's that value such that the area to the right is alpha. Okay, so it's not really a percentile when you define it like that, but there is a relationship. And let me just highlight that for you quickly. If the area to the right is alpha, so that's some value between 0 and 1, obviously, then that means the area to the left is just 1 minus alpha, because all the area needs to sum to 1. Okay, so let's just have a look at the definition of a percentile before I get back to that. So remember, the 100th percentile is some value eta p such that the area to the left of that value is equal to p. Now in this example, the area to the left of Z alpha is 1 minus alpha. So in other words, p is equal to 1 minus alpha. Okay. So if we substitute 1 minus alpha everywhere where we have a p, we get this line. So the 1 minus alphth percentile is eta 1 minus alpha. Okay. So remember, the area to the left of this value is 1 minus alpha. And I told you earlier that the area to the right of this value is alpha. Therefore, the area to the left of Z alpha is also 1 minus alpha. So in other words, you can restate Z alpha. You know that it's equal to eta 1 minus alpha. They're exactly the same value. So if I rewrite this statement here with Z alpha, then I can say the 100 1 minus alphth percentile is Z alpha. Now, a little bit more formally, we can rephrase that definition of a percentile like so. If alpha is a number between 0 and 1, as it should be, then the 1 minus alphth percentile of a distribution is that smallest value, Z alpha, such that the area to the left is 1 minus alpha. So remember, under this notation, Z alpha is that value such that area to the right is alpha. So therefore, the area to the left is 1 minus alpha. So these Z values have a special name. They are called Z critical values. This is an important term and it's going to be especially relevant in the second semester. Table 4.1 shows some percentiles and Z alpha values. So the 90th percentile corresponds to a Z alpha where alpha is 0.1. Okay, so remember for the 90th percentile, you have 0.99 to the left and 0.1 to the right. So 1.28 is exactly your Z alpha for 0.1, and it's also your 90th percentile. So if you think of this, for example, that 0.05 is a percentage. So you have 5% on the right, 95% on the left. So obviously the same value, and in this case it's 1.645. Okay. Example 4.21 is just another demonstration of this concept. So the 95th percentile is that value. So the area to the left is 0.95, and your Z 0.05 is that value. So the area is to the right is 0.05. So it's exactly equivalent to the 95th percentile, which is 1.645. Now remember, due to symmetry, if you come across on this side, this value here is minus 1.645. Okay, which is exactly minus Z with an alpha of 0.05, and this is just the 5th percentile. This brings us to the end of this video. I hope you enjoyed it. Enjoy the rest of your day.